We are going to talk some more about internal resistance. We're going to do some adding of resistances in series and parallel, and maybe, if you're lucky, we'll get into circuit diagrams. Here is a problem on internal resistance made by our good friend Mike Dickinson. So pause it and solve this problem. Hopefully you've done it. And you realized that this 9 volts, that is our EMF, because it's the largest voltage that you would get before you plug anything in. This 8.6 volts, that is our terminal voltage. That's the slightly disappointing voltage you get when you actually plug stuff onto the circuit. It's always lower, the EMF. You should realize then that you lost some voltage, and you just subtract this 8.6 from the EMF, and you see that you are losing 0.4 volts to the internal resistance of the battery. That's kind of bad. So it's asking you to find this internal resistance. Hopefully you remember that the voltage lost is equal to the current through the whole circuit and the battery times the internal resistance. And you plug in your numbers. You lost 0.4 volts. It tells you that your current is 0.02 amps. And your internal resistance is that little r. If you solve for it, you get 20 ohms. How about that? For series and parallel circuits, let's make a drawing that we're going to call figure 5.8, and let's start, oh, it's blue, hey, with a series circuit. You've got resistors that are one after another, with a wire flowing through all of them. Let's call this R1, R2, and R3. And here's the current. We're going to call this I. Now, an important thing to note is that each of these will have a voltage, but all of these voltages will add up to give you a total voltage of the circuit. So let's say you had 1 volt and 1 volt and 1 volt. Total across here would be 3 volts. If we're looking at the resistances, that's also easy. They will add up to give you your R total. Let's say you had 20 ohms, 20 ohms, 20 ohms. You get 60 ohms total. That's because more resistors are all going to be slowing down the electricity going through the circuit. The current, though, through each resistor is the same, meaning that if you have 1 amp going through one resistor, you have to have another amp going through the next resistor. If we have something a little more complex, which is a parallel type of wiring, let's say we've got 1 resistor, 2 resistor, 3 resistors. And let's call this R1, R2, and R3. We've got total current coming in here, but then it's going to split to I1, I2, and I3. Currents come through to the right. We can say that the voltages this time are the same, because if this guy here is at 110 volts, so is the middle guy, and so is the third guy. For resistances, they do something funny. They add up so that the total, or the 1 over the total, is equal to 1 over the resistance of the first, 1 over the resistance of the second, and 1 over the resistance of the third. It's a funny way of adding things up. And the result is that your total resistance is less than R sub 1, or R sub 2, or even R sub 3. Meaning that as you add more resistors, you actually lower the resistance of the circuit. It's sort of ironic, but you're opening up more pathways along for the electricity to flow. And as far as current goes, the currents add to give the total. Meaning that if you have 1 amp, 1 amp, and 1 amp, your total current would be 3 amps, because they all combine to make one giant amount of electricity. Circuit diagrams. These are easier than IB Bio. Woohoo! The symbols especially. Let's start with the symbols that you're going to actually use. A lamp. It's an X. If you have a switch that you can turn on and off, it just looks like this. If it's open. If it's closed, it just looks like a wire. You've got a voltmeter. You might find this hard to believe. This is a V with a circle around it. An ammeter, call me crazy, but I'm going to say that's an A with a circle around it. If you have a resistor, which is a box with a line going through it. I used to remember drawing them as a squiggle, like Charlie Brown's shirt, but the IB doesn't seem to like that. They like boxes, which I'm fine with. A variable resistor, or you might call it a potentiometer, is going to be a box, just like your resistor, but then it has a connection that comes onto it, and this would go off somewhere else. And equally as useful as all these would be a battery or a cell, which usually just looks like this. Sometimes they put multiple ones together to look like that. Very common. Ones that I find within the IB used less often is an AC power source for alternating current, a galvanometer, also don't see very often, a heating element, also fairly rare. Oh, also a transformer. It's not more than meets the eye. It's actually a very strange looking symbol though. For stepping voltages up or down. And that's it.